Welcome to tutorial 17 in the Practical RF Design tutorial series. I am Dr. Prakash Sangaran from Innowave. In this tutorial series, we will learn the complete design and optimization guide for a 4G and 5G antenna. In part 1 of this tutorial, which is part 15 of Practical RF Design with Keysight ADS tutorial series, we learned the antenna introduction, antenna selection and PIFA antenna design. In part 2, which is part 16 of Practical RF Design with Keysight ADS tutorial series, we learned part 1 of antenna optimization. This is a continuation of part 16. So if you haven't watched part 16, please watch it first. In part 17, we will learn the continuation of PIFA antenna optimization using Keysight ADS. We have created the parameters to be optimized in the tutorial 16. In this tutorial, we start by inserting the parameters into the appropriate microstrip schematic components, as each unique parameter is created for each microstrip component. As you can see, I am inserting the correct parameters into the respective microstrip lines. If you can recall, previously we defined the default value with unit mil. Due to this, the microstrip schematic components should not have the unit on them. Otherwise, they will have double units, which will result in wrong width and length parameterization. Due to this, the correct way to insert the width and length parameters into the microstrip schematic component is by double-clicking the component and inserting it. While inserting the parameters, the unit will disappear. Since our intention is to get rid of the unit, we can ignore this. Each component parameter is inserted individually by double-clicking on it to launch the Edit Instant Parameters. There is a shortcut way to quickly edit the component parameters. Before this, we have been clicking Apply and click OK after updating each component parameter. However, it is adequate to just click Apply. After clicking Apply, the parameter will be updated for the microstrip component. Instead of clicking OK after that, you should select the next component and modify the width and length and click Apply. This process can be repeated to accelerate the updating process of the microstrip component parameters. As I speak, I am demonstrating this process now. I have given a unique number for each microstrip component's width and length to identify them easily. This way, I am able to update them quickly. I will fast forward this process because it's a repetition. As you can see, I am inserting the ground plane dimensions now. It's not parameterized because I am not planning to optimize the ground plane size. We have completed the insertion of parameters to the appropriate microstrip components. Next, MSUP is inserted to define the layers of the PCB. This is a 4-layer rigid PCB with the antenna located on the second layer. After inserting MSUP, enable CON1 in all MSUP because that's where the layer is defined. CON is our top layer, followed by M2, the second layer. Next is M3, the third layer, and finally CON2, the bottom layer. These layers are defined in order from MSUP1 to MSUP4. Since we decided to place the antenna on the second layer, M2, let's move the microstrip lines or antenna to the M2 layer. This is done by changing the substrate to MSUP2. I am manually changing the substrate of each microstrip schematic component to MSUP2. Since this process is repetitive, I will also fast forward it. As you can see, we have moved the antenna from the first layer to the second layer. Before moving to the next step, it's a good practice to check and make sure all the parameters are correctly inserted. Our schematic is ready. Finally, we can create and update our ADS layout from this schematic. This is done by clicking Layout, Generate or Update Layout and click Apply. The layout is successfully generated and it looks exactly like the way we want it to be, which is a good news. We have a trace on the top layer connecting the antenna from the second layer. Due to this, we need a VR for this connection. I could have done the VR connection in the schematic, but I choose to do it in the layout. You can connect the VR in the schematic as well. To place a VR, go to Insert VR. By default, through-hole VR is available. Change it to specify top or bottom layers and select the second layer as the bottom layer. Your cursor now has a VR. All you need to do is place the VR at the right place. Since we created our layout from the schematic, we should check if our layout is parameterized by going to EM, Components, Parameter. Under Design Parameters, you can see all the parameters that you have created in the schematic. The next step is to set up the EM simulation. We will launch the EM setup and choose our preferred EM simulation setup. However, there is an error message here. It says that no ground plane was found in the substrate definition. This can be fixed in the port editor. Right now, two ports have been found, but P2 is actually the ground reference pin of the P1. So drag P2 and drop it in the ground of P1. The issue should be resolved now. Let us set up our optimization. FEM EM simulator is chosen for the simulation. Let's define the frequency range and frequency points of interest. The frequency range of our interest is 0.5 GHz to 4 GHz. I want to add a few frequency points to the simulation as well. These are single frequency points which I would like to get the results. Let's leave all other settings to default. We can save and exit the EM setup. Finally, we create an EM model by clicking EM, Component, Create EM Model and Symbol. Let's create another schematic to place the EM model and optimize it. Drag the EM model and place it on the schematic. I don't like the layout lookalike symbol created by default, so I will change it to dual port symbol. To place the S parameter simulation controller and port one shot, click on Insert Template and select the S parameter template. I am deleting the unnecessary components in the schematic, which is the display template and also the term 2. After that, the term 1 is connected to the EM model. The S parameter simulation controller frequency is defined next. Similar to the EM setup, we set the frequency range to be 0.5 GHz to 4 GHz. The frequency step we are setting is 100 kHz. Next, we have to redefine the parameters for optimization. To do this, we need to insert the var or variable and equations component first. After that, we need to redefine the parameters again. I will redefine the parameters in the same order for simplicity. The x and y in the EM model are redefined as a and b in the var respectively. The number behind is the same between x and a and y and b. The values of x1 and a1 are equal, the values of x2 and a2 are equal, and so forth. In the same way, the values of y1 and b1 are equal, the values of y2 and b2 are equal, and so forth. Since it's a repetition, I will fast forward the parameters redefinition process. After that, insert the newly created parameters into the EM model. After modifying one parameter, press Enter to arrive at the next. This parameter redefinition is done because the optimization can only be done via a var. I will fast forward this process as well. Next, on the var, we have to enable optimization and set the optimization range for each parameter. Each parameter will be assigned an optimization range with minimum and maximum values. Since we are doing continuous optimization, there is no step value to assign. Since I have another template done with this optimization range setting, I won't complete this process because it's lengthy. The last step before starting optimization is placing optim and goal in the schematic. Optimization controller or optim and goal can be easily searched in the search all libraries by just typing optim and goal. Set the goal to optimize S11 to be less than -10 dB across the frequency band of interest, which is 746 MHz to 960 MHz and 1.71 GHz to 2.69 GHz. When entering frequency, the unit should be entered together. Since we have two different frequency ranges, each frequency range will have a separate limit. With this, all the steps required for running an optimization have been successfully completed. Next, we have to click a button to run the optimization. Since the parameter optimization range definition is not completed in the schematic, I will use the schematic I have completed the parameter optimization range definition. Just click on Optimize button to start the optimization. With this, the optimization section of the antenna design and tutorial 17 comes to an end. I will see you in the tutorial 18, which will discuss the next topics, antenna EM simulation and the results and analysis. Thank you for watching tutorial 17. For inquiries, please email pragash@innowave.co or visit www.innowave.co.